All right, so in this video, we're going to be looking at calculating the Fourier coefficients using the definition for an odd function. We'll do an even function and a function that is neither even or odd in another example. But here we're going to be just looking at our odd function. So the function that we're trying to model is the f of x equals x, and we'll do the interval negative pi to pi. And then, of course, it's periodic after that. But on this main interval, it's x. And so on this primary interval, it is odd. Now, this is our general Fourier series that we end up with. So we have our a sub 0 plus our sum of a sub n cosine n pi x over L, and the sum of b sub n sine of n pi x over L. And so what we need to calculate is what a0, an, and bn need to be in order to model this function. And so these are our formulas for a0, an, and bn. So we're going to just go through the example. L in this case, since our interval is defined to be negative L to L, L is equal to pi. So that's the first thing to fill in. So as we fill in our a sub 0 formula, we're going to fill in our pi everywhere there is an L. And we'll replace f of x with x. Now, if we go ahead and calculate this, keep in mind that, again, we're going to try to use symmetry in order to simplify the math. Because this is an odd functions integrated from negative a to a are 0, and therefore a sub 0 is 0. So again, we don't want to actually do the integration if we don't have to. If there are properties that we can apply, then we want to apply them. Now, the next one we have to calculate then is the general a sub n. And so again, we'll replace our L with pi everywhere. And our f of x with x. And that's going to give us 1 over pi. The integral from negative pi to pi of x times cosine. Since our pi's are going to cancel, we just have nx. But cosine is an even function, and x is an odd function. And when you multiply an even function together with an odd function, you get an odd function. And so if I integrate from negative a to a for an odd function, I also get 0. And so I don't have to do that integral. But I do have to do bn, and we'll see why in a moment. So again, I'm going to replace my L's with pi's everywhere. And my f of x with x. And of course, that is going to simplify to 1 over pi from negative pi to pi. Oops. of x sine, again, when the pi's cancel, nx. So this is the integral we have to integrate. Now, sine is an odd function, and x is an odd function. When you multiply two odd functions together, you get an even function. And so, in fact, if you were to go to the graph, for instance, of, as an example, x sine x, just for like the first term for our series, you're going to end up with an even function. You'll see that the graph is symmetric with respect to the y-axis. So, because if you multiply a negative by a negative, you get a positive and so forth. Everything will be symmetric. So we can take advantage of that symmetry and we can simplify our limits of integration a little bit and multiply our integral by 2 and then integrate from just 0 to pi of x sine nx. Dx. Now let's actually do that integration. So this would require integration by parts. So I'm going to let u be x and dv be sine nx dx, and then du is dx, and v, we're going to integrate v, and when you do the antiderivative of sine, you get negative cosine, and then we also have to undo our chain rule, which would multiply by n, so this will be 1 over n. And so when we put our equation back together again, let's see, we've got negative x over n, that's our uv, cosine nx, from zero to pi, and then minus the integral from 0 to pi of v du. So negative 1 over n cosine nx dx. And so if we integrate that one more time, the negatives will cancel, and I'll get a plus. And I can pull the 1 over n out front. And if I integrate cosine, then the antiderivative of cosine is sine. And I will get another 1 over n. And again, I have to plug in 0 and pi. Now, so let's think about what happens when I start plugging in 0 and pi. So my first we have 2 over pi. We'll come back to that later. Now if I plug in x, pi for x, I get negative pi over n. But then when I plug in cosine of pi, n times pi, cosine n pi, and then I'm going to subtract, which means minus minus 0, because it's 0 over n times cosine of, okay, I'm plugging in 0. So that's going to kill that one. And then I have 1 over n squared, but then sine of n pi, and then also minus 1 over n squared sine of n times 0. So that's 0. That's definite. Sine of 0 is 0. Any whole number multiple of pi of sine is also 0. So that's also gone. And so all I'm left with is this piece. So 2 over pi times negative pi over n. And then cosine n pi, when n is 1, it's going to be negative 1. And then when cosine is even, then it's going to be positive 1. So if I'm starting with n equals 1, because that's what our formula says. If we go back up here, Bn starts with n equals 1. So then I can combine this negative 1 to the n with this negative out front, and I can cancel my pi's, and I end up with 2 over n times negative 1 to the n plus 1. Because the pi's cancel, I'm left with n. This negative is absorbed here, and then I have the 2. And that's equal to my b sub n. So now what is my Fourier series? So let's fill in our general formula. So a sub 0 we established was 0. And a sub n we established was 0. So all of this, poof. And what do we end up with b sub n? We end up with 2 over n times negative 1 to the n plus 1. And so what we'd like to do is we'd like to graph this and make sure that this makes sense. So in order to see if this graph works, we're going to fill out some coefficients for various values of n, starting with n equals 1, and then we'll see how that builds toward our graph. Now, if I plug in, this will be my pi, and so this will be nx. All right, so when n is 1, I'm going to get 2, and then this will be a positive because it's 1 plus 1, so it'll be an even power, and then sine of x. So 2 sine x, and then the next term will be minus 2 over 2 will be sine 2x, and then 2/3 sine 3x, and minus 1/2, because 2/4 sine 4x plus 2/5 sine 5x, and then 1/3, right? When n is 6, that'll be 1/3 sine 6x dot dot dot. Now let's see how we do. Now, if we go to Desmos, we can start filling in some terms. So I've already filled in some terms here. So now the next one would be 1/2 sine 3x, and then minus, what was the next one? It was 2/5. No. 3. It was, never mind. Minus sine 2x, and then it was 2/3, and then it was 1/2 minus 1/2 sine 4x, and then plus 2/5 sine 5x. And let's do our last one, 1/3 sine 6x. And you can see that what's happening is, if I compare this to y equals x, so again, in this window where we're comparing from negative pi to pi, we can see that this section, as I add additional terms, it is more and more and more closely approximating that y equals x function. Of course, it's periodic. We're imagining it as being periodic. And so because our sine and cosine functions are likewise periodic. And as we keep adding additional terms, we get better and better and better approximations to our y equals x function. So the graph is doing exactly what we had hoped that it would do.